This is Coral Cove, an active ecosystem divided into 4 monitoring sites: Seagrass Meadow, Coral Garden, Rocky Channel, and Sandbar Lagoon. Before any change occurs, we have a clear documented baseline. We know the exact sediment depth, the turbidity of the water, and the result of a timed count for juvenile fish populations. Then, a coastal storm rolls through the cove. In the immediate aftermath, the environment shifts. The water grows cloudy, with suspended particles, and the ocean floor physically moves. For a 4th grade classroom, this shifts the focus from guesswork to evidence. Students step into the role of junior coastal scientists, using concrete measurements to explain what happened. Post-storm data reveals one trend across all 4 sites. Every timed fish observation is lower than the baseline. The most common assumption is that the storm itself drove away the fish. To maintain scientific rigor, students must identify the boundary of that data. The count is lower after the storm, but one timed observation cannot prove the storm was the only cause. This teaches students to navigate uncertainty, separating a visible pattern from a proven, isolated cause. To track how the ocean floor moved, students use this equation: subtract the baseline sediment depth from the afterstorm depth. At Rocky Channel, the depth moved from 0.8 centimeters to 0.3, yielding negative 0.5. Students translate that sign into physical direction. A negative result means erosion, while a positive result indicates deposition. They also learn to evaluate those numbers without bias. A negative sign indicates direction, not that erosion is bad, just as positive deposition is not automatically beneficial for every habitat. This turns abstract decimal subtraction into a defensible environmental argument, rooted in actual data translation. Once data is analyzed, teams must build a response plan to address the cove's changing conditions. The response is built under a strict constraint. Students have $500 in fictional planning units. As they select action cards, they must decide what to prioritize and what to leave in reserve. They debate trade-offs, predict how their actions might affect future evidence, and identify the gaps in their own understanding. For an educator, facilitating this level of open-ended scientific debate requires a high level of preparation. The simulation provides this through a 20-minute teacher confidence guide, structured daily playbooks, and controlled releases that keep evidence secure until students are ready to analyze it. This structure allows a teacher to manage a predictable, scaffolded classroom environment while students grapple with a complex, unpredictable mystery. Late in the mission, new follow-up evidence arrives that directly tests the students' response plans. Every team receives feedback tailored to their specific choices, revealing one benefit of their plan and one remaining pressure point in the cove. This feedback prompts a shift in language. Students strike through absolute claims like "the storm caused" and replace them with scientifically accurate phrasing, "conditions changed after." By the final session, students demonstrate the intellectual flexibility to revise a claim when confronted with new facts. The mission concludes with an individual coastal science brief authored by each student. For an administrator, this brief provides a rigorous, accessible artifact that documents a student's ability to interpret data, identify cause and effect, and communicate uncertainty. It offers a consistent way to make complex scientific reasoning visible and measurable across an entire school or district. Bring the Cove into your classroom. Explore it at patienslearning.com.